Well, hello and welcome. So I thought I would do a little video and talk about sheet metal. So there's a lot that goes into it. You probably wouldn't think much of it because you can model and not know a lot of the principles behind sheet metal modeling. But most likely where you work, you're going to probably need to know some of this math that goes into it. So the biggest thing really is, some companies, they may make you create these parts via flat patterns and then have them folded, or vice versa. You may make it and then just simply unfold it. If you're just unfolding it, it's not going to be a big deal. You can probably ignore most of this, but it still comes in handy to know, just kind of to help you visualize how it could be fabricated, a sheet metal part, how it could be, created in a meaningful way, or even potentially, if you're really into parameters, you can actually drive a lot of these flanges and their sizes based on the numbers you're given. But the general principle of it, and I kind of made an example here just to show y'all, and it's very simple, is a part like this. So whenever I made a sketch, all I did was like an L shape, and it's pretty straightforward. You hit finish, and then in Inventor, which is what I'm using here, you can do like a content or contour flange, and it creates from that contour shape that I chose that shape. Now, granted, I could flip it to either side, but what it's doing is it's taking the general properties that I have set and applying them to this bend to match that shape. And that's pretty much what you do with sheet metal. The reason sheet metal is used so much is because it's let's see, how do I say this? It's a part that you'll use a sheet metal. Okay, you'd use sheet metal to make a part that would then fill in an area that you can't use a general standard part for. So like when you're out in the real world, you may see a bridge and you see structural steel everywhere, like I-beams and channel, angle, all that cool stuff. But there's always plate like sheet metal in there to unite the parts, because you can't have a standard piece of everything. Sheet metal is basically that glue in between any design. There's going to be a lot of things you make custom. So, you're always trying to fill a void, essentially. But, yeah, so if I were to go and look at my sheet metal defaults for this one, for instance, you're going to have all kinds of cool math here. But the general premise is you have an inside radius that is set, and then everything is based off of it and the thickness. So, I just chose the defaults here. Not much to talk about really, but like you're always going to have an inside radius value, and then naturally your outside radius value will equal the inside plus the thickness. And that makes sense because you're looking for, if it's a flat part, it's going to have to be consistently the same thickness all the way across, And just for reference, here's what my flat pattern would look like. And what you're seeing, these dotted lines here, those are actually where the bend begins and ends, and then this is actually the center of the bend. But like basically, if you're looking, a lot of people when they're drafting, when they're new to it, they're not really looking at the part as something being physically made. In a perfect world, everything can be created, but at the end of the day, no, some things cannot physically be created with machinery at a company or possibly in the world. It depends on what you're making, but there's a lot that goes into sheet metal besides just the actual practice of making it. You have to start thinking about the real design of the part. So that's why they give you all this information, is because at some point you may have a problem where like the edge of that is too close to here and they can't physically bend it or something like that. So sheet metal is one of the more complicated things, and there's a bunch of classes I teach on this, but this is just a little demo to kind of get you going. And if you're not familiar, check out the sheetmetal.me website. It's one of my favorite places to talk about sheet metal because it's got everything. So just take a quick look here. So you can tell just by default that they have a pretty great breakdown of all of this on the Fabrication Formulas tab. I think that I'm just on the main one. Yeah. So what you've got is a flange, which means like an overall, width basically on a fold, and then a leg would be like to the start of the bend, and then they actually denote that the dimension that you would want for that bend itself is just the outside setback. Now that's a really easy formula, and the reason I say that is because if you look at it, Assuming that it's just, you know, in this shape right here, a perfect 90, it's going to just be radius, you know, so because your radius for your circles both have a center point right here. So that's pretty straightforward. And then, you know, you've got your thickness for your part, and then you have a given angle. And basically using these little values here in the inside radius, you're going to be able to produce the dimensions for what that part would be, flat or other. So I'm going to go to each section, but if you want to see all that in the main area, you can check it all out on the Fabrications formula. And like I said, I would check this the whole side out because there's some good stuff, and I'll point it out in a little bit, the design guidelines and whatnot. But I'm going to start here with inside setback. So, you know, these two tabs, this and outside, are pretty much the same with descriptions for each listed. And I would suggest going through and just reading all of this. But, you know, it's really cool to see a metaphoric projection of what this looks like. So, like, if you were to draw a non-sheet metal part, you would have everything come to this point right here. You know, you'd have sharp edges. But when you're making sheet metal, it folds, so you end up losing that metaphoric end, you know. So you still have those technically, like even when you're drawing, you'll have a point there whenever you're making your fillets and whatnot if you're doing it on a sketch. So, you know, like the general idea basically is when you're making something, it's not going to have sharp edges in sheet metal unless it's, you know, like the actual end. But you can figure for it if you ever need to draw it back for whatever reason. And they have calculators, so, you know, for me, I'm not a math person, so I tend to let the formulas work for me, because, you know, in Inventor and SolidWorks, both, you can put in these formulas in equations or parameters, and it'll spit out everything. You just put in the numbers. So for me, I would just type in, you know, tan and then blah blah and bend radius. I'm not gonna actually go through and physically calculate that, because that would suck. Plus, what if you change it, you know? But it's good to know that you have these options here for it. And as you get better at it, you'll start to really work on designing things. So like in this case, it shows, you know, if you made this part imperfectly, you would end up with these sharp edges like we talked about you wouldn't have. But if you wanted to go and ensure that this part went end to end like this, you would end up having these fillets. But then when you're making sheet metal, there is no round edge. You know, you're working with, as I showed a second ago, flat edges. So if you're working with flat edges, you wouldn't have this round part. It would just end at the beginning of that bend, so it would cut back to here. Now, technically, this one could stay there, but it'd be really hard to fill that weld, so they kind of just showed the example of trimming this part here too. But, you know, one cool thing about working with these 3D programs is a lot of times they will trim themselves back, depending on what features you're using. There's a lot of ways to make any sheet metal part, but I will later make a video on how to use the tools best. So, but for now, you know, take note of how those work. And like I said, this is the same. So if you want to go through and read it, go ahead. The next big thing is bend allowance and bend deduction. So, you know, you kind of saw earlier, you had the leg and the flange, and then you had outside setbacks on both. But if you're working with the flat pattern, and your company that you end up working at, it actually requires you make the things flat, then you're going to have to use this all the time, bend allowance and bend deduction. And essentially what it's showing, if you look here on bend allowance first, we have the two leg dimensions and a really, really random overall dimension. And basically what's happened here is this area here, the orangish area, is actually the arc length, essentially, of this curve. So basically, if you were to quantify the distance from the end of this leg to the end of this leg, when it's flat, this is what it would be. And, you know, the formula for that's kind of crazy because of that. You got pi over 180 times the bend angle. Yeah, okay, I didn't see the angle sign. Times the inside bend radius, K plus K factor, times material thickness. So there's quite a bit of stuff to that. And I'll talk about the K factor in a minute. Usually, you're not going to have to manually figure it. Wherever you work, there will be a set K factor. I think in Inventor, for instance, I think it defaults to a 1/2 inch. Let's see. 0.44. Yeah. So at the company I worked at, it'd be 0.44, and then if it was a rolled circular part, it would be a 1/2 inch. So anyway, If you were to look at the other end of the spectrum, you have bend deduction. Now what it's doing is it's taking the overalls, our flange dimensions, and it's subtracting out the difference there. You know, you can see like there's overlap. So like, you know, you're pretty much just figuring out from that direction. It depends how you want to model things and dimension them, but ultimately I tend to lean on bend allowance a lot. But if you're modeling things the proper way, you don't really have to ever figure this unless you're doing it flat, which I mentioned earlier. Other than that, you do have some charts on here. And you've got your bend angles, and it talks a good bit about this. And this is good stuff to know too, especially when you're working with parts that may change the angle when you're working with them. But you have your excluded and included angle, and your formulas are based upon those. But you know, in an ideal world, you've got like this guy, a perfect 90, but it's not always the case. You know, sometimes you may have some kind of object coming off of something else, and you got to have it positioned a certain way, and that's when sheet metal gets a little crazier, because then you got to really work on how you draw things. So keep that in mind. And then the last thing here is K factor. So I mentioned it, but basically the idea is you've got like a theoretical neutral axis, and that's how they bend the part is, you know, upon that K factor. So, you know, if you want to read about it, you're welcome to. Like I said, it's pretty much a set amount, but you know, there are some references here for people, because technically the K factor is different for every material type. Now where I work, they kind of just generically went with one K factor type, and I'm sure a lot of people do, because it would be very hard to quantify the various K factors so you would have consistently and not mess up. But you know, it's good to know, because this is a formula piece that's used in like every single formula. You've got K factor, but odds are, you know, you'll just be given a number and you'll just roll with it. So but that's it. I didn't want to keep this long. If anybody has any questions about it, just let me know.